So our next talk is entitled HPC Platform Efficiency and Power Savings for Large-Scale Workloads, and it's going to be delivered by Martin Hilgeman from Dell Technologies. Martin joined Dell Technologies in 2011 after having worked as an HPC application specialist for 12 years at SGI and IBM. In 2019, he joined AMD as a senior manager and worked on porting and optimizing the major HPC applications to the ROM microarchitecture. Martin returned to Dell Technologies in May 2020 as the HPC performance lead and distinguished member of the technical staff in Dell IGS. He owns a master's degree in physical chemistry obtained at the V University of Amsterdam. So without further ado, I'll give it over to Martin.
Yes, thank you very much, Mustafa. Let me share my screen. Unfortunately, I was not able to present in person. So
we just get the presentation set up on the screen. Just give us a minute, please, Martin. Sorry about that. Can you please share your slides?
It says host disabled participant screen sharing, so I'm allowed to share.
Okay. Yeah, we're going to look into it. It's all set now. Can you try, please, one more time?
Yes, I think I can do it now. Okay, I think you can all see my presentation right now.
Yes, we can.
Okay. Today, what I want to talk about is how we can save power when we are doing MPI messaging, as we are aiming, especially for large-scale workloads, to run as efficiently as possible. The power consumption of your workload is becoming increasingly important. And in this talk, I would like to present to you some of the work that I've been doing in order to look for opportunities to save power when we are doing MPI, especially on applications that are having a slight load imbalance. So firstly, about my group, I am part of the Infrastructure Solutions Group, ISG, and inside there is also HPC hosted. And what we do in HPC engineering at Dell is 4 major things. So we actually design, develop, and integrate the HPC solutions that we put out. We call them DVDs in Dell terms. So these are tuned reference architectures for various HPC application segments like research computing, oil and gas, manufacturing, and life sciences. Then we also do a lot with partners, and that can be, for example, universities, it can be Dell Solution Centers, it can be our suppliers, where we look for opportunities to improve our HPC solutions and to do HPC development, research, and engineering as a whole. We also do that inside Dell, and that is where we work together with our CTIO group. So what we put in future systems, and with our platform engineering group, where we actually test drive new solutions and test their applicability for HPC. Lastly, we tend to publish a lot of our studies on the internet. You can visit hpc@dell.com, and there you can find a wide selection of white papers, blogs, and presentations that our group has been doing. A lot of this work is taking place in the HPC and AI Innovation Lab. And we can also invite you there to run. We have various partners that also run there in our lab and Tesla Workloads. Same for customers. And we also use that to host technical briefings and give tours as well. So what I've run here, as said, the study was on the clusters in the HPC Innovation Lab. It is a very big lab, also for American standards, where everything is bigger. So more than 1,300 servers, tens of petabytes of HPC storage. And what I'm showing here are two of our clusters. We have more, but I've run on our Intel-based cluster that is running the latest generation of the Intel scalable processor, the Sapphire Rapid liquid-cooled. And we have on the AMD side, we have our Minerva cluster that is running the latest AMD Genoa. Both are equipped with InfiniBand networks. So to set the stage a bit about where I'm coming from, let's talk about collective MPI functions, because these are the functions that are the most network intensive and also are the most compute intensive for either the host or for the GPU if you offload to the GPU, like Gilad presented in his previous talk. There are various collective MPI functions, as we know, and the most intensive ones are all reduce, all gather, and all to all, where everyone is sending messages to everyone that is taking part or participating in the same communicator. We also know that if you look at how your application is performing, and here you will see a area chart where I am plotting wall clock time against the MPI rank, and then I'm doing a breakdown between the application and the various time spent or the time spent in the various MPI functions. You see here a spike in extra application performance, computation time, sorry. So there is a load imbalance here on these nodes. Whatever the reason is, it can be a poorly performing node, it can be poor decomposition across the nodes, for example, in the application. But what you see here is when you look at the yellow area, that the collective MPI functions tend to spend a lot of time fixing the load imbalance in your application. So you see here very little time in all reduce, whereas the other MPI ranks show significant time in the MPI all reduce. If we look at a different application, for example, the MOM5 Ocean model, where I've run on 80 nodes of AMD with HDR200 InfiniBand, again, application time in green, and you see that there is a slight imbalance across the ranks. And you also see that there is varying time in the yellow all reduce area. If we zoom in to this all reduce area and we distinguish between what I call wait time, so where we are waiting for other ranks to also start the all reduce, and we then also distinguish the execute time, which is the actual data transfer, then you can see that the data transfer itself is a very, very small portion of the time spent in your MPI collective function. So the overhead is, well, it can almost be not to be taken into account because your network apparently is fast enough because we don't see any time there. What we are seeing here is the load imbalance that is the cause of the parallel scaling overhead, and also the reason maybe why your application is not scaling. If we then look deeper into the statistics of my MPI profiling tool, then I measured 123,000 all reduced calls. 190,000 of them were less than 64 bytes. That is a problem in a lot of HPC applications, and what you want is to change these applications and change these all reduces, if possible, by their non-blocking brothers and sisters, so that you can hide the communication time by overlapping with computation. You also see here the load imbalance. So the minimum total time spent in all reduce was 191 seconds. The maximum time was 463 seconds. The actual transfer itself was 18 seconds, obviously, for all MPI ranks. So that is less than 10% of my total time spent. If we then look at the OSU all reduce benchmark, then we can see for various MPI libraries. I've also I've put FFH2 and the other major ones in here. You can say that completion of an all reduce for a sizable cluster, although these days 2000 MPI ranks is not much, then you can see that the completion takes anywhere between 10 or 20 and 40 microseconds. That, I think, gives us the opportunity to add a few extra microseconds because it's already taken some time. And with that, extra microseconds are a lot of extra cycles. And in these cycles, we can maybe do something smart. So let's look into that. We then look at possible power savings, and we start with what we always do when we run applications. Then we think, okay, my application is running. It is utilizing all the cores on my node. As you can see with the top commands, all cores are 100% busy. So it looks good, you think. But actually, when you look deeper and you attach a debugger to your application, and this is an OpenMPI backtrace, but all MPI libraries tend to do the same, you can see that it's in a barrier, and then what it is then doing, it is then executing the progress engine that is tracking the completion of the barrier. And that that loop is very CPU intensive, where the core is constantly, or the MPI rank is constantly polling the fabric for incoming data. So what happens schematically if you have a load imbalanced application, and here I have core 1 and core 2, which are both working on their own chunk of computation 1. When core 1 is done, it sends a message to core 2, for example. But my core 2 is still busy. And that means that core 1 has to wait. So it is blocking here for core 2 to finish its computation and then sends the acknowledging receive. So this wait time is the polling and the CPU intensive part that you saw on the previous slide. Now, I've been thinking, can we do something smart? Can we, for example, when we are doing this and we run at typical base frequency, or maybe we run slightly higher because of we have extra thermal headroom. Let's assume that when core 1 does its send, that while it is waiting in the send, it clocks itself down to a lower C state, for example, 1v2 gigahertz or something. That means that extra power budget becomes available on the CPU socket for the other cores. Maybe these cores are still busy, and then they have the potential to clock up their core even more because of the extra thermal and power headroom to finish the remainder of its computation quicker than before. And this could yield at the end a possible speed up. So that is a kind of ideal scenario where I'm looking at, or maybe we can save power. I mean, we can hopefully improve performance. If not, then at least we have saved some power. So what I'm doing here is that I want to test this. So I have a proof of concept where I am writing my own MPI functions. So for example, the MPI receive function that you see here with standard arguments. And what I do is that I intercept the call. When I'm in my own routine, I clock the core down to its lower C state, for example, or whatever it is. Then I do the actual receive of the data, and I call the real MPI function, so the PMPI function that is used internally in and part of the MPI standard. Then when that's done, after the receive, I then clock my CPU back. So I bump the clock speed up to its nominal clock speed, and I resume business as usual. That's the idea. And then I preload this library into my application. So that means that I don't have to modify either my application or my MPI library. I just preload my own function, and then I call the real MPI function that is provided by mVabbage, for example. Okay, what can we do when it comes to C state selection? We know that we can do it in the operating system through to the sysfs interface, for example, but there are also smarter ways to do it. What we can do is that we can use specific instruction set extensions, and this is x86 only, so it's not ARM. Both AMD and Intel have released extensions to the x86-64 instruction set. And these instructions can be used to force the CPU into a lower C state when it is, for example, waiting for an interrupt or for an event to complete. This event can, for example, be a signal, as I said, or it can be that it is monitoring a write to a memory address. So when it is seeing a write to a memory address, then it can execute the actual wait instructions. These are CPU vendor-specific extensions, so they are not interoperable between both x86 CPU vendors. They both have their own way of doing it. What Intel has, and we know that already for quite some time, is that we have the monitor and the mwait instruction pair, where monitor watches a store operation to a memory address that can wake up the CPU. And mwait, if you call that instruction, then it will put the CPU into a lower C state. Now, the problem with monitor and mwait is that they can only be executed in ring 0, so only in the where the operating system, that the kernel actually runs. So no way to call this from the user level. The latest Intel CPUs, so Alder Lake on the client and Sapphire Rapids on the server side, they have the umonitor and umwait instructions. So it is U of user. These can be called as an ordinary user, and they have the same semantics as the monitor and mwait instructions. And what you do is that you control this instruction through to a specific register, where you then manipulate this register where you set certain bits. So you can set bit 0 to set a certain C state, and then the rest of the available bits, they are there to set the number of clock ticks that the CPU should sit in this lower C state. So you can actually tune this as a user, where you have a maximum value because you only have 30 bits available here. The way that you can use this is as follows. If you have a recent compiler, for example, GCC 12, I didn't find them in earlier compilers, then they have intrinsic functions. So they have underscore umonitor and underscore umwait. And then you need to compile with a special flag so that the compiler actually generates the umonitor and umwait instructions. On the AMD side of the world, it works quite similar. They also have an instruction pair. It's called monitor X and mwait X. It is already there for quite some time. So in the 15th generation of the AMD architecture. So I think that was Jaguar or something. It was before Naples and Rome for sure. And the semantics are slightly different. So again, you have a part of the register that is there to control which C state you're going to run. Then you can specify in another register whether you want the CPU to be woken up by an interrupt or by the write of a memory to a memory address. And as the Intel UM wait, you can also set the wait time in TLC clock ticks that it should sit in this and wait lower C state. And it works quite similar. Again, you need a recent compiler, and there are intrinsics that you can call then with a special flag so that the instructions then are being generated. You have to be careful because a library that is compiled with this flag will not run on Intel and vice versa. So you have to be very specific here where you compile and run. Okay. The way that this then gets into my MPI library is as follows. Let's assume that I'm starting with my all reduce, and with my all reduce, I firstly want to get a request handle, and I want to track the completion of that request. I am then calling my monitor instruction and a memory address that I am watching for a write to. Then in my all reduce function, I am doing a non-blocking barrier so that I get my request handle that I want to monitor. And then I continue. Well, you would say, okay, why are you doing a non-blocking barrier and not a simple rewrite to a non-blocking collective like I all reduce? Well, I've done that, but the performance is quite a bit slower than when I do it in this way for some reason. I think MPI all reduce itself is very, very well optimized, and maybe I all reduce is less optimized. I'm not sure, but this way of doing it is significantly faster than when I use a non-blocking collective. The same when I do it for a point-to-point function, but then it is easier because let's assume MPI receive. I then just do a non-blocking receive to get a request handle. And for MPI wait or wait all or wait any, I already have a request handle. So that makes it far easier to do anything there to save power. Now, when I now have my request handle, I go to the next stage. And then I do an MPI test, which immediately returns, of course, and it tracks the completion of my request handle. And you see that the completion of my MPI test is written to my flag variable that I was monitoring before with the monitor instruction. So when my test returns 1, that means that the request is complete, then the monitor will stop and wait. So if my request is done, then if it is not done, then it will do an end wait of a certain amount of cycles and tests again after the cycles, your cycle period has been completed. If my request has completed, then I call my real function. So that's the way that I've done it. So what does that mean? Sorry for the animation, I was working on this. If I do an all reduce and I add my library that is doing the end waits on top of it, I noticed that it's adding an extra 6 microseconds to my latency for all reduce. And for other collective functions, I've looked at all to all as well. It is similar. You would argue, okay, 6 microseconds for very small messages, that is actually a lot of overhead because here, for example, it is increasing the latency significantly. However, when I run and with larger messages, then the overhead is just nothing. So then it can be very beneficial, you can say, for large messages, but you have to be careful with small messages. But here, I am not taking any load imbalance into account. I also looked at the total time spent in the end wait for various functions. This was a large simulation of 128 cores, 128 nodes of an ocean model, 16,000 cores. And I noticed, and I measured the time spent in the M weight itself. And you see that it varied a bit. So my all reduce was less than 1/10 of a second per all reduce. That implied, you can say that there was a big load imbalance again that had to be recovered by my all reduce, and the weights itself were already quite efficient. Okay, are we actually saving power? That is then where it is all about. And the way that I've done this is as follows. I have run 2 MPI collectives. I've run the OSU all reduce and the OSU all to all for a message size of 1 kilobyte, because I think that all reduce is widely used, not only in HPC, but also in AI. All to all is very important for a wide range of HPC applications, and it's the most communication intensive one that we have. Then what I'm doing here is I am artificially putting in some load imbalance in my OSU all reduce and OSU all to all, so that then I can be assured that my M weight is actually doing something, and then I can measure the power that I'm saving while I am in my polling engine or in my progress engine. I tested on latest Intel, Sapphire Rapids, and AMD Genoa. The Intel is using InfiniBand NDR. The AMD systems are using InfiniBand HDR. And I measured the power of my CPUs every 250 milliseconds, so 4 times per second, using the Dell F1 count internal tool. So to start with all reduce, you can see here that I am plotting 2 CPUs, here CPU 0 and CPU 1, and here is the power consumption on the vertical axis. So standard behavior is full TDP power consumption of 350 watt while it is in the all reduce routine. When I am applying M weight, then I'm saving between 55 and 60 watts of power. You can also see that the frequency is not lowered. So if you compare that to a system level, OS level C state selection, where you go to C3 or maybe even higher, then I'm actually clocking the CPU down. Here, that's not the case. So I'm still running at my nominal and even at a turbo frequency, because this is a 2 gigahertz part, and I'm running at 2.9 more or less. Same for all to all. I'm seeing the same behavior where I'm saving power, and I was seeing something funny that I need to investigate further. That the power consumption was at the end going up using the MFAPIC implementation of all to all. If I compare the behavior of my all reduce with other MPI libraries, so I've looked at OpenMPI and Intel MPI, you can see that Intel MPI you're doing something very, very smart. So they are saving even more power in the all reduce than what I am doing with the M weight instructions. For the rest, for the other libraries, I can really see that my M weight is certainly saving power. And you see that the frequency that CPU was running was the same for all MPI libraries. I'm seeing something similar for all to all, although Intel has not optimized all to all power consumption in the same manner as they have done for the all reduce. So here, using M weight actually helps, and I was getting the most power savings in OpenMPI and MFAPIC when I was running M weight. What about AMD? AMD actually showed more power savings than Intel. So the way that the AMD CPU is designed, it's designed very aggressively to save power. I don't know the exact details. It's been a few years, but I mean, it is very impressive that you can save 30 watts. And for comparison here in blue and red, I've also looked at enabling the MFAPage to blocking mode. So where we are just doing blocking. So we are putting the MPI rack to sleep instead of polling. That actually saves more power. But we know from using blocking mode that your performance is abysmal if you enable that. And here on the AMD side, when I apply M-weight, I am actually saving power. And also at a lower frequency. And same for all-to-all, where I'm actually saving even more power. So that is quite impressive. On the Intel side, or Intel MPI side of the world, where I am comparing the MPIs, I can see here that my Intel MPI is again for all reduce doing something, something very, very smart. I didn't see that in the all-to-all that much. And here utilizing the M-weight, and I'm again seeing the funny behavior of the MFAPage M-weight, something that I didn't see with other MPI libraries, but I am saving power nevertheless. You can also look in AMD at the power consumption per core. They have a special performance counter for that. And you can see if I measure power per core, and this is on a different AMD Genoa, and you're plotting here power consumption for all 64 cores, that it goes down for all reduced from 2.6 to 2.7 watts per core to 2 to 2.4 watts per core for MFAPage. For all-to-all, it is considerably more. So instead of 5 watts per core, I am down to 2 to 2.5 watts per core if I utilize the M-weight. Now, what does this mean for application-specific performance? And I realize that I only have a couple of minutes left. I looked at 5 applications, 5 applications that are known to have some load imbalance, that are known to do a lot of collective MPI functions, and I wanted to have a set of applications that have a different communication pattern. So we know from HiCom and MON5, which are ocean models, that they have a nearest neighbor communication pattern and are doing primarily all reduces. We know that OpenFOAM is point-to-point and very small all reduces. And the chemistry side of the world, where we have quantum espresso in material size, we are doing a 3D FFT, which means a MPI all-to-all because of the global transpose, and the same actually for this particular CP2K dataset. When I then look at the Intel HiCom ocean model, you can see here where I have as is compared to my M-weight that I am saving approximately 38 watts per CPU. And it is costing me less than 2% of performance. So I would say that is actually quite impressive. When I look at the AMD side, it's actually even better. I showed the significant power savings on the AMD side already. You can see that here it is. It's more than 40 watts for a 280 watt CPU, and in this case, it actually made my application go 10% faster compared to my standard HiCom run. This was with MFAPage 2, by the way. So you can see if we do this, that we can have the best of both worlds: power savings and performance improvements. Here's the MOM ocean model. You see, and the picture is power savings at the expense of a very small performance loss. But I would say this is quite small. And here you see the Intel, where it is slightly faster, and I am saving performance. And when I look at OpenFOAM, it didn't work as well as I had hoped. I am saving power, but I am slightly slower, as you can see. So, but still 25 watts per CPU times a lot of nodes adds up quickly. And I'm only looking at the CPU, so I have not measured other parts that are dependent on the CPU load, like the voltage regulators, for example. So it can be even more in theory. On the AMD side, again, saving power is slightly slower. And to conclude with Quantum Espresso and CP2K, it's the same thing. I'm saving power. You can also see here that the CPU frequency goes up and down a lot. And on the AMD side, same thing, saving power is slightly slower. And I've also have put a different mode for CP2K. This is the standard way of running it. So I am slightly slower and I didn't gain anything. That can also happen when I don't have a load imbalance. And this is another implementation where I'm actually doing the non-blocking collective instead of my iBarrier. And you can see that it is saving more power, but it is considerably slower than my baseline. So that is not something that you would like in real life. So to conclude, I think this is very interesting. You can see that using these instructions, specific instructions for the architecture, they can give power savings up to 17%, or you can get at least a 10% in most cases, or large scale workloads. And you can at the same time, sometimes at the expense of a little performance loss. And here you see the Intel and AMD graphs where I have normalized against my standard performance, and higher than one walk clock time means slower. Lower than one power means power savings. So you see that there are power savings across the whole board for both architectures, more on AMD than on Intel. However, sometimes on the AMD side of the world, it is also costing me a bit more performance compared to Intel. That concludes my presentation. I hope that you find it useful. Thank you for attending it. And again, apologies that I was not able to present in person. Hopefully, that's something for next year. Thank you.
Thanks, Martin, for the great presentation. And we got a question.
Hi, can you explain whether you use the lower power state, regardless of whether you actually are the last one to join whatever the barrier operation is? Means you really don't know at the time you lower your power state, right? For every rank.
Yeah, but I am lowering. I'm lowering the power state on a per core level.
Okay.
So it's not per CPU socket; it is per core, and that makes it very, very powerful. So that means that the last core to arrive at the barrier still has its nominal power state.
Okay. Now, assuming the last one arrived, every core you're using is in the lower power state, right?
Yeah.
And itself will detect that the barrier has been reached by everyone, so you back up to a higher power state?
Yeah, so what I'm doing is I do the MPI test that tracks the completion of my barrier. So when the last one has reached the barrier, my request is marked as completed, and then the CPU power state is resumed for all the cores to its nominal power state.
Okay. Do you have any idea I guess from the power lower state in the last one drive, and then you do the test in the lower power state, then wake every core up, how much extra latency that introduce?
I think that's something that I should measure. I think it is a few microseconds. Yeah, so it's a balance. And what I didn't show in this presentation is I showed you that I can actually specify the amount of cycles that my core should sit in the lower C state. So I can set it up to 2 billion cycles, which is 1 second, right, in nominal 2 gigahertz world. So that is something that you can play with.
Okay.
And I've only just started exploring this. So there are a lot of tunables. There is a lot of extra intelligence that you can get out of the system. For example, it would be nice if you can track load imbalance early on, and that you then already can provide hints to the MPI layer that you're having load imbalance, and which MPI functions actually have load imbalance, because most applications in HPC side of the world you're doing the same iterative thing over and over again. So if you can have something that can actually recognize what you're doing, then you can do smart things.
Okay, thank you.
Let's thank Martin again for the great talk.